Okay, valence electrons. There are valence electrons and there are core electrons. And so the valence electrons are in the outermost principal energy level. In terms of the floor, they're on the, in terms of the hotel, these are the ones on the highest floor that has any electrons on it. So if there's electrons on the 3rd floor and there's no electrons on the 4th floor, then 3rd floor electrons are it. And it's all of them on that floor, because it's like if a tornado came and took off the top of the hotel, right? See, in your imagination, anything can happen. Can you tell I grew up in the Midwest? So a tornado comes and just takes up the top of the hotel, and it gets the top floor with people on it, right? They get taken away. Those are the valence electrons. Everybody lower is going to be safe, and those are the core electrons, okay? So the core electrons, highlighting in the wrong place, the core electrons are those in the lower floors, the lower energy levels. The valence electrons are really important in understanding how atoms behave. If we look at the periodic table and we look at the electron configurations, here's hydrogen and helium, etc. So here, lithium and beryllium both have the highest occupied level is level 2, right? And so lithium has 1 electron in there. It has 1 valence electron. Beryllium has 2 electrons on that 2nd level. It's got 2 valence electrons. And as we go over, we're adding an electron, 3, 4, 5, 6, 7, 8. This number up here, 3A, 4A, that tells us how many valence electrons the elements underneath it have for the main group, right? Transition metals follow their own rules. But for the main group elements. So you're in group 7A, you got 7 valence electrons. Okay. So write an electron configuration for phosphorus, identify the valence electrons and the core electrons. How many electrons do we have to do? 15, thank you. 15 electrons. I'm going to draw the orbital diagram first because I kind of like orbital diagrams. So there's 1s, and on the 2nd floor, 2s, and 2p. And on the 3rd floor, we've got 3s and 3p. And I think that's going to be enough space. So I'm going to use red, because I don't know why, but the book uses red for electrons. And so I'm going to count. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. We can write the electron configuration from that. 1s2, 2s2, 2p6, 3s2. And how many are in 3p? 3. So that's the electron configuration. Which energy level is the highest one that has electrons? 1, 2, or 3? 3. It's the highest floor in the hotel that's got anybody staying there. Nobody's in the 4th floor yet, but these guys are on the 3rd floor. It's all of the electrons on the 3rd floor. So it's all of these guys. How many is that? 5. And if we look at the electron configuration, we're looking for the highest big number. Well, 3 is the highest big number. 6 is the largest small number, but that doesn't matter for anything. So those are our valence electrons. So there are 5 valence electrons. What are the core electrons? Everybody else. Let's maybe make them blue. So these are core electrons. When the tornado takes off the highest occupied floor, it's going to leave those guys behind. They're going to be safe. So these are the core electrons. So VE stands for valence electrons. CE stands for core electrons. How many core electrons are there? 10. 2 and 2 is 4 plus 6 is 10. Or count them. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Any questions? This takes some practice before you remember it, but the hotel seems to help most students. Okay, so where's that information hiding on the periodic table? So we can divide the periodic table into 4 different blocks that represent filling of those 4 different quantum sublevels, S, P, D, and F. So here it is. So the period numbers, 1, 2, 3, etc., those correspond to the principal quantum numbers. So this is n equals 2, n equals 3, 4, 5, etc. In a way, helium should be over there, right? And he isn't because he's a little guy and he's so cute, we let him break the rules and hang out over here because he actually behaves a lot like these guys. But this block sticking up is 2 columns. How many electrons can fit in an S sublevel? 2, because there's 1 orbital, right? Over here, there are 6 columns, and that represents the P block, a P subshell, which has 3 orbitals and can hold 6 electrons. How many orbitals are in the D block? 1, 3, 5, right? It's odd numbers. 1, 3, 5, 7. So this has got 5 orbitals. That room in the hotel has 5 beds. How many people can stay there? 2 in a bed. 10 electrons. Look at this. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And F, 7 beds, 14, right? I won't count those for you, but that is 14. So what I think is so incredibly cool about this is Mendeleev made up this arrangement just based on the properties. Organizing so properties fell into columns. And then many years later, after a lot of other elements are discovered, we come up with quantum mechanics. And they didn't make quantum mechanics to fit the table. The table wasn't made to fit quantum mechanics. They both fit together because they're just both what nature is. Isn't that cool? That's just crazy. So the whole ordering business is all hiding here in the periodic table. So the way you can do the ordering is you just start at the beginning. So here is 1 in the S block, so that would be 1s. And then this is 2s, and next would be 2p, and then 3s, and this is 3p, and this is 4s, and then what about these guys? Okay, so those are D block, and so that's n minus 1. So if this is n, these are n minus 1. So 4 minus 1 is 3. So this would be 3d, and then this is back to regular 4p. 5s, here's n minus 1, 4d, 5p, 6s, and this is where things get a little more wonky. So look at this, 57, 72. There's a bunch of numbers missing. Where are they? They're down here. our periodic table on the wall is actually how it should look. So why do they do this to the periodic table? Well, I think because it's a better aspect ratio for a piece of paper. Honestly, I think that's why it is. Also, these guys are mostly radioactive or extremely rare, and so we don't end up using them much anyway, so they're just kind of down there as, kind of a footnote. But it's part of the periodic table. And so the D block elements were n-1. These are n-2. So if you look at the periodic table here, that the transition metals, don't they look like they sunk down from where they should be? So if we erase this, because that's not how it is. It's going like this. Oops. What happened? Okay, it came back. It's going like this. You kind of think, well, this should be up here, right? And then this would be 3D, but it sank. Just like the valley floor is sinking. Did you know that? We're pumping all this groundwater out, and the floor of the valley, the basic elevation of the valley is slowly getting lower. Yeah, that's kind of a problem. And so here, I imagine also, well, these guys just sank further, right? So these are n-1 because they sank, and these are n-2 because they sank more. So this is 6s, and there's 1 here, and we're just going to kind of skip over him and do these guys. So n-2, this is coming from row 6. 6 minus 2 is 4. So this is 4f, and we get back to these guys, n-1, 5d, and this is 6p, and 7s, and 5f, and 6d, and 7p. The good news is you don't need to go down here very often. Any questions? You have to practice it a little bit, but I think it's a lot better than memorizing how to draw the things out and make the lines. So writing electron configurations from the periodic table. This is doing chlorine. Okay? So if we're going to write the electron configuration for chlorine, if we want to do the inner electron configuration or the noble gas configuration, we're going to go up to the next row and go to the end and find that noble gas. So we're going to say, well, we'll take the electron configuration of neon, and then what's coming after that? Well, after that is these two guys. That's 3s, 1 and 2. So that's 3s with 2 electrons. And then we come over here, 1, 2, 3, 4, 5. 5 electrons in the 3p. That make sense? What if we want to do the whole thing and not take the shortcut? Why would we want to do that? Just humor me. Let's do a different color. Well, if we're just going to start at the beginning, here's 1. This is the S block, and that guy's not where he's supposed to be. But 1s, 2. And then we're going to go 2s, 2. And then over here, this is P. P is 1, 2, 3, 4, 5, 6. 2p, 6. And then here, 3s, 2. 1, 2, 3, 4, 5. 3p, 5. So you can read the electron configurations off the periodic table. A lot less remembering. S, P, D, and F, and you can tell where these blocks are because they stick up. Right? So here's a more regular periodic table that's not all color-coded. But we could identify those blocks, right? So this is the S block. And over here, because helium's misbehaving, that's the P block. Here in the middle, what's that one? D. I'm losing you. And this down here is F. So if you need to know how many electrons could fit in an F sublevel, just count the boxes. It's 14. Okay, so how do we find the electron configuration of bismuth using this periodic table? Well, first of all, we have to find bismuth, right? It's down here, it's number 83. I think we want to do the noble gas configuration, right? Because that's going to be a lot of stuff. So here's bismuth, and to find the noble gas, we're going to go up and to the end. So this is the noble gas that's next smallest, right? So then we've got xenon in brackets. What comes after xenon? Well, we're going to come over here. This is 6 in the S block. 1 and 2. So that's 6s2. Okay? This would be 5d, but then it jumps, and so we're going to keep those guys together. Sorry about that. Over to here. And so this is F. We're working on the 6th row, but we have to subtract 2. So this is 4F. And we go all the way across. Oops. Go all the way across. I won't make you listen to me count to 14. Okay? So there's 14 electrons there. And now we're going to get back up to here. So we're in row 6. That's n equals 6. The D block sank down, and so this isn't 6, it's 5. So 5D, and we're going to count those electrons. There's 10. Over here, we're back to the main group. This is not sunk, right? And so this is 6 again. 6P, and how many electrons? 3. 1, 2, 3. Okay? Any questions? Let's get some more practice here. I'm not going to do chlorine because chlorine was on a previous example. So let's do silicon first. Find silicon. What's the previous noble gas? Neon. So for silicon, we're going to start with neon. And then we're coming over to this row, the 3rd row. So this is 3, the S block, 3s2. And then over here, 3p2. Okay? Strontium, Sr. Okay, that's down here. What's the previous noble gas? Krypton. So, krypton, and then this is what comes after krypton. This is row 5, and we've just got 2 here in the S block. So that's 5s2. How about oxygen? Oxygen is up here. Let's do the whole thing for oxygen. So starting at the beginning, we've got one S, and the other guy's over here. So that's one S2. And then this is 2S, and we're counting across 2. And then we come over here to 2P, 1, 2, 3, 4. 2P, 4. Any questions? It takes a little practice, but you can do it. Okay, so all of that being said, there are some irregular electron configurations. Basically, you need to know that these exist, and I'm going to try to give you, some kind of reason for why it happens. So we know that the 4s sublevel is lower in energy than the D, and so the 4s fills before the 3D. But then some of the noble gases, the transition metals do some funky things because, they're all squirrely anyway. So this is what happens. These are what we expect from what I just taught you, and these are what are found experimentally. There's no predicting this. They just studied them and found that this is how they are. I only expect you to remember the first two. Okay? So let's do this. Let's draw the orbital diagram for the electrons after the noble gas. So there's the 4s. And then the next room is the 3D. It's got 5 beds. So that's 3D. So if we look at chromium, we've got 6 electrons to stick in there, and this is what we expect. We expect 1, 2, 3, 4, 5, 6. That's what we expect. But that's not what it does. So these are very close in energy, and electrons are really cheap. They want the lowest energy, but if it's 5 cents more a day to go to that room and have your own bed, right? So this guy moves up over here. Now, what's nice about that orbital diagram? It's all half filled, right? This room is half full. This sublevel is half full. So that's like a Groupon deal, right? If you fill up these 2 rooms half, then you get this discount. Groupon deals are weird, right? Well, what about copper? Well, copper's got 11 electrons. So here we've got the 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Well, this is another situation where this electron is going to be over here instead. And if you're into things being nice and symmetrical, this one's half full, and that one's completely full. Half full and completely full are a little lower in energy than other combinations. So it does that. And then these guys are just kind of weird. I can't rationalize those for you, so